Our theme song, Paradox by Odling, has a BPM, that's beats per minute, of approximately 60. With every beat, 5 hours of video have been uploaded to YouTube. This volume and velocity demand algorithmic solutions, as it would take a small army of people to watch it all. Forget about coming to consensus about what they saw. This is Data Skeptic Consensus, and the 26th installment in our series in which I take a wide liberty on what falls under the consensus umbrella in order to discuss the great paper Video Anomaly Detection by Estimating Likelihood of Representations. Yuqi Ouyang joins us to discuss in just a moment.
Hi, I'm Yuqi, currently doing my second year PhD study on University of Warwick. My research focuses on video anomaly detection using recent neural network advances or deep learning techniques. And for video anomaly detection, is actually trying to use a model to kind of remember what is happening in a fixed camera scene, to remember the normal actually. And then when the abnormal events happening and when we need to discriminate.
When I learned about anomaly detection in the classroom, it was taught to me in like kind of picturing an industrial setting where maybe there's a temperature sensor and a pressure sensor and you're taking regular readings of these things. And of course, temperature can go up and down with time and pressure does as well, I guess. But anything that was maybe one or two standard deviations away from the moving average, we could consider an outlier in very, very basic statistical way. And I guess that can work in simple situations, but how does that scale up to a multi-dimensional problem like video?
For anomaly detection, I think its application is already a lot of applications going on, especially in industrial. So video anomaly detection is actually focuses on surveillance videos, which means the scenario is totally different. For surveillance videos, you are not only need to focus on object appearance, but also you need to focus on object motion information as well. I think that's the most differences.
Do you approach it from a supervised or an unsupervised point of view?
Normally, for video anomaly detection, I think there's a lot of deployed system for video anomaly detection, such as those cameras which can detect if your speed is too much or too high. I think for those applications, they are supervised, I think. But for video anomaly detection, so the scenario is kind of different when you don't know what is actually an abnormal event happening in a scene. So which means you don't have enough data of abnormal events, which means most of the data you have is only normal data, which means people are just doing normal events in those things. So video anomaly detection currently, I think most of the research going on is focusing on supervised learning, which means you use normal data to train a model, and then when abnormal events happen, the model need to respond.
Well, framing the question in that way, and we say that, here's examples of normal cases, find things that don't match this. It sounds very intuitive until I think about the actual implementation. How do you go about something like that?
I think for implementation, I think basically when you train a model with normal events, kind of have a value of abnormality, and then you, based on the value, you can set out some threshold. If for test video clips, you put the test video clips into the model. If the output anomaly value is higher than the threshold, maybe it is abnormal. That's the case, I think.
That abnormality value is very interesting to me. If we did it in some very crude way, just like histograms and things like that, I'm afraid it might detect things like lens flares, or, I live in Los Angeles where it doesn't rain too much. Maybe a rainy day would suddenly be an anomaly. How do we get the system to give us something that's more intuitively pleasing than these sort of base level changes?
So I think normally when you train a model, that model often focuses on one thing, which means focuses on one environment. And I think it cannot be used for another environment, such as if you train a model in Los Angeles, I think the model should be only used in Los Angeles.
I presume you don't try and represent the video as, in kind of its raw form where you have a high, volume and velocity of data. It has to be compressed or transformed in some way. Can you describe some of the procedures to turn this raw data feed into something more consumable for machine learning?
When we have a video clip set, normally we can say that something going on in the video normally clip, which is, I think there are two things can represent what is going on in that video clip. One thing is that how the video clip looks like. Another thing is that how the video clip, how the objects is moving in the video clips. So that is actually what we call this spatiotemporal information. So actually, you can do is that when you have a video clip, what we can do now in deep learning techniques scenario, you can do is that you use a model to break down the dimension of that video clips into a low dimensional latent space. Then you can say that in that low dimensional latent space, you have some spatiotemporal information going on, which is actually some features.
Are there common data sets that you and other researchers collaborate and focus on when you do analysis like this?
Mostly use the datasets are three datasets, I think. One dataset is called UCSD pedestrian dataset, which is from Hong Kong. Another one is the Shanghai Tech dataset, which is actually from Shanghai. And another one is actually Avenue dataset, which is also comes from Hong Kong. There's one new dataset actually came up recently, which is developed by Microsoft. But I don't think so much researchers works on that data set. But I think it's a better data set to test the robustness of your model, actually.
It'll be exciting to see how that gets adopted then. And what are some things that would be considered anomalies in those data sets? I'm picturing pedestrians, maybe a person falling off of a bicycle. That would be hopefully anomalous, shouldn't happen too often. But what are the kinds of events you're looking and hoping to find?
Yes, so I think for those datasets which focus on pedestrian way, I think normally the abnormal events mostly focuses on maybe you ride a bicycle on the pedestrian set, which means you are abnormal object, and you ride a car on the pedestrian way, which means you are abnormal as well. But I think for Shanghai Tech dataset, the abnormal event, which is more complex, they kind of have a fighting scene, and which is more complex. I think there are one more dataset actually, which is focused on the crime, but actually crime dataset is really, really difficult for abnormal event detection actually, and I don't think so many researchers doing it. But I think the ultimate goal is actually to test a model for crime dataset because we are focused on surveillance videos.
What would a abnormal event in a crime data set perhaps look like? Is this, somebody running out of a bank with a big bag and a dollar sign on it in their hand? Or, what kind of crime events can you detect?
Mostly it's robbery, I think fighting, and I think there are different, actually, a lot of scenarios going on. Yeah, I think mostly it's robbery and fighting, I think.
You were saying that the crime data sets are hard to do research on, that it's a tricky problem. I guess I understand on a theoretical level, but then if I just compare it to, okay, what if we don't use an algorithm, but we use a human annotator? Probably they could provide us labels at a greater cost, of course, not automated. But why are human eyes able to find anomalies like a robbery or fighting, and yet for algorithms it's currently a research challenge?
It's difficult because I think for the spatiotemporal information for crime especially is not so discriminative, I think, for an algorithm. So that is the reason why it is so hard. Because for crime, I think it happens in a short of time, I think. It is hard to detect for an algorithm, I think.
I'd love to dive deeper into the spatiotemporal features. It makes very intuitive sense that those would be useful in this. I'm curious about how you're able to form features around that, particularly something like temporal features, naturally comparing the current state to 30 seconds ago or yesterday, same time is useful. But how do you set up feature engineering pipelines to deliver on ideas like that?
If you are using representation learning, if you break down the dimension of video clips, I think most time you are doing is you can set up a time stride, which means you take up certain numbers of frames in the video clip and then you put it in your model. If you're using autoencoder, which means the feature comes out after the encoder, actually.
Could we talk a little bit about the soft clustering work that is one of the main contributions of the paper? What do you apply and why was that a major step forward?
Actually, people have done hard clustering before, but I think it was trying to do a soft clustering because soft clustering is actually more accurate than hard clustering. And the thing is that if you're considering clustering in a low-dimensional latent space, the thing is that you're actually drawing some areas which can put those data points into those areas and saying, okay, those data points belongs to the areas. If you're doing hard clustering, which means the area is kind of deterministic, I think. But if you are doing soft clustering, which means those areas are more dynamic, which will represent those belongings with probability values.
Well, I've done a little work with systems, autoencoders and systems like that. In particular, in natural language processing, I've used BERT, which will take any amount of text you give it and give you a fixed length vector of numbers. But I can't make heads or tails of those numbers directly. They're useful to me in machine learning, but I can't really interpret them precisely. Do you have a similar situation in your work, or do you have some intuition about the way in which the dimensionality is extracting and highlighting the key features?
You can think that for low-dimensional features, they have some dimensionality numbers which are actually decided by you. So I think from my point of view, from my experiment, if you set dimensionality number too much, and if you're using autoencoder, and then I think for those numbers in the features, in the low-dimensional features, they are so close. You can think like in low-dimensional space. If the space is kind of a large number of dimensional space, then those data points are very close, which means it is not so easy to use soft clustering technique to kind of clustering those data points, because if you're using Gaussian mixture model and EM technique, and those data points are so close, and then I don't think the covariance matrix are going to work.
And when you generate some results with your methods, how do you go about evaluating them? If it's an unsupervised method, it's going to produce some results. What's the ultimate metric of success?
In this research community, we mostly, and the majority of the researchers use area under curve to estimate how good your model is actually, which means if the area under curve is high, so the maximum is actually 100%. And yeah, we compare the model use area under curves.
I think that's a great metric in the sense that it's going to reflect both your false positives and your false negatives. But where do you get your ground truth from? How do you end up saying of the test cases which were true anomalies and which were false positives?
For video anomaly detection, we have labels actually. So the first kind of label is actually based on the frame level, which means you take out a frame in a test set. The frame is actually labeled with ground truth, which means it's abnormal or normal. Another one is actually on a pixel level, which means you take out the frame and you can actually know that all the pixels in the frame is abnormal or normal pixels.
And can you contrast your results to some of the other techniques and approaches that you compared it to?
I think now people are kind of chasing advanced algorithm now, so which means each year the performance get increased a lot, actually, I think. I don't know about this year, but for my model, I think the performance is actually okay in terms of performance. But the novelty, as you know, the novelty is actually not so great.
When you look through on a case-by-case study across, this time series where you're measuring the abnormality of the scene, if we were to watch the video where there are peaks, what sorts of things do you see that, to your eye, are differentiated from the normal period?
So that is about how you actually see the abnormality, I think. The thing that we can generate an error map or kind of a heat map, which depends on your model actually. If your model generate patches, or maybe your model is generate pixels, if the model is so accurate, then we can compare with the generated pixels with the ground truth pixels, so we can see the differences. And when we use the whole frame of a video, and then we can do is that we compare the ground truth frame with the frame you generated, and then we can generate a heat map or something. Then you can see what is happening, what is something high anomaly or what is something low anomaly.
And broadly speaking, we were talking about area under the curve. Could we compare and contrast some of the empirical results? The performance of your approach is pretty good compared to the other methods. How does it perform, and what's the class of contenders like in general? Are we at a good state of the art with these types of tools?
I think a good value of area under curve should reach 90%, I think. So as you can see in the most used and the most difficult dataset is Shanghai Tech, and not so many models achieve 90% on that dataset now.
And to my ears, 90%, I mean, it's a long way off from perfect, but pretty good score just out of box, I guess. Is that because most of the scenes are sort of mundane and boring, and the simple day-to-day life is easy to predict, and the outliers are just a little few and far between? Or how should I interpret that number?
I think in general, if your model reaches 90%, maybe you can say your model could detect most of the abnormality in the data set. But there are also some progresses that you can do actually that. I think 90% is a good value, especially for new data set. 90% is a good value.
I'd love to dive into some of the figures you have in the paper. I know it's almost impossible on an audio format to do this, but looking at myself right now, figure 4, in which you're visualizing some of the manifolds you calculate and then laying across them the amount of outlierness that's been labeled by the algorithm. For me, it is a promising result because it shows that things that are considered anomalies are in the same manifold space in certain areas. Could you share some of your thoughts and interpretations and why that was a useful analysis?
The figure is really interesting because if you are using the autoencoder and if you're using, for example, reconstruction error, which is actually calculated by your produced result and the ground truth, the things that normally you're using autoencoder to reconstruct those video clips, the thing might happen is when you are using a normal clips, it might happen that the reconstruction error is actually high. And if you are using an abnormal clips and the reconstruction error is sometimes low actually, which means autoencoder is not the perfect technique to do. But if you're looking at the latent space distribution using soft clustering, and the thing you can say is that, okay, so mostly we can see is that, okay, so many clips break down the dimension into the latent space, but most of the data points are actually low, and there are just kind of few or not so many data points are having high error, which kind of makes sense because for those data sets, the abnormal ground truth is actually the number of abnormal ground truths is actually low, not so many. So which means we kind of pulling the distribution away between the normal and abnormal, so we can see things more clearly.
When I look at the overall pipeline used in the project, we didn't go in too much to the object detection side, but at the front end you have that, and the autoencoders and the reconstruction phase and the clustering that we've gone through. These are all kind of novel steps in the process, and the overall architecture makes a lot of sense to me. Where do you see as the main areas to focus future research to take these things forward?
As you can see, we use the object detector, which means we are kind of using some filters to filter out the objects, but object detector can make some errors, which means sometimes it do misdetection, and sometimes maybe it's the detection is not so good. For the future, I think what I'm doing now is actually we don't use object detector. We get rid of that, and we're kind of using a model on whole video clip. We don't crop out those objects now. I think that is the most the priority things we're doing now.
So when you take that out, I guess you have a closer access to the raw data. So with that, maybe the benefit of it doesn't lose something in translation where the object detector makes mistakes, but it also takes on a bigger burden for your project to kind of either fill in the gap of doing something like object detection or, I don't know, another methodology entirely. Can you give us a preview of how you approach that?
I don't use the object detector now, which means my model is actually working on a full video clip, pixel by pixel, actually. It's no way to say for my model now, actually. But the thing is that for object detector, the thing is that, so currently, actually, object detector is really convenient, and you can say that because it is actually trained very well. But the thing is that the object detector is not trained on my dataset. It's actually trained on those open set dataset, which like Microsoft Cocoa, those dataset. If you're using those dataset and train the model, and then you are using the model on those abnormal event dataset to crop those objects out, which means something bad is going to happen.
Well, there's been a lot of focus on, I guess, the social and political level of, not just how these things can be done algorithmically, but now that we're hitting such big achievements, 90% and higher AOC, that these are viable tools that can be used in government and policing and these sorts of things. What are the broad ethical concerns around technology like this?
So, as we all know, that current research going on video anomaly detection is based on unsupervised learning, which means that you are actually training the model with only normal data, and then hopefully the model can respond on abnormal data. But because your model is actually trained on normal data, which means the scenario could happen. The scenario is actually false detection, especially false positive detection, which means the person is actually doing something all right, but your model says, okay, the person is actually doing something abnormal. So I think that's the biggest issue if we are kind of pushing all those research into a deployed system. And not so many researchers focus on that actually. Okay, if you think the model is actually trained in a supervised way, okay, we train with the abnormal event and then we detect the abnormal event. Okay, then the model shouldn't make so much error on respect to the false positive detection, but the case is not.
And I know this is a bigger question than our discussion, probably your research, but do you have any thoughts on how to address that? Do we need human-in-the-loop requirements or standards of some kind? What are some of the constraints that might be smart for us to consider?
If you're using a model and if you're using a test video clips, and then for the model, I think the model should not say it is normal or abnormal. I think the model should say, okay, it's normal, and maybe we can take a deeper look or something like a catchy area, or kind of let the model to look again or look more clearly, and then the model can see, okay, it's abnormal or it kind of looks like it's abnormal, but I want to see again. That is the thing, I think. We need to make those kind of catchy area.
So use the tool as a informative guide of how to prioritize where a human reviewer goes in, something like that?
Yep.
Well, Yuqi, thank you so much for coming on the show to share all of your expertise and your research.
Thank you. Thank you, Ka.
That concludes this installment of Data Skeptic Consensus. Our guest today was Yuqi Ouyang. Claudia Armbruster is our associate producer, Vanessa Bursiaga does guest coordination, and I've been your host, Kyle Polich.